Okay, so for our next topic within stoichiometry, we're going to be taking a look at moles. And so moles are a tool that chemists use to figure out how many particles we have in a given mass. So let's pretend that you're working at a lab and you have to try to make water. Well, you know that you need to react 2 hydrogens for every 1 oxygen, but how much mass does that mean? We can use the mole to figure that out. So take a look at this drawing of paper clips. If I was to ask you, okay, how many paper clips are in this drawing, it would take some time for you to figure that out. That's the problem that we have with atoms. Because they're such large quantities within a very small mass, it is inconvenient to count them, and then again, all these large numbers can be confusing. And so what chemists decide to do is decide to make packets. So taking a look again at our paperclip analogy, let's say we have 144 paper clips, scattered across the table. This would be very hard to identify that you have 144. It would be a lot easier to figure that out if, for example, you had 12 packages of 12. And so if we make sure to always lump our paper clips into these packages, it's a lot easier to figure out how many we have just by looking at them. And again, we can call this package a dozen. That's just the name for 12 of something. And to figure out how many paper clips we have, we could divide however many paper clips we have by the package, and that could give us a very easy number of packages. And again, if we want to go back around, going from packages to individual paper clips, we would multiply that by 12. Taking a look at atoms, we can do the same thing. So remember, diameters of atoms are measured in angstroms, which are 10 to the negative 10 meters. And so if the average height of a beaker is 10 centimeters of water, you can imagine that converting between 10 to the negative 2 and 10 to the negative 10 meters can be tricky. And so chemists do exactly the same thing that we did with the paper clips. They package their atoms together, but this time in packages of 6 times 10 to the 23. So 6 times 10 to the 23 packages in one package, and we call that a mole. Just like a dozen is 12, a mole is 6 times 10 to the 23. And again, to convert between packages and individual atoms, same thing. If we have a whole bunch of atoms, to figure out the number of packages, we divide by 6 times 10 to the 23. And then if we want to go the other way around, let's say we have 2 packages, we would multiply that by 6 times 10 to the 23. Now this number that I keep repeating is known as Avogadro's number. It can be represented as an L with just an L, or a capital N with an A subscript. So I usually use capital N with an A subscript, but either are used. Okay, so we've sort of decided to use these packages of things to make it easier to count. Now let's talk about using those packages to figure out masses and vice versa. Let's say 1 dozen paper clips is 8 grams. So 1 packet of paper clips is 8 grams. That is the unit mass. It tells us how many grams is 1 unit, 1 package. And so if I have a whole cluster of paper clips, all I have to really do to figure out how many I have is to weigh them. Okay, so here I'm drawing a whole bunch of paper clips again, and to figure out how many packets I have, which will then tell us how many overall I have, all I have to do is take that mass, divide it by that unit mass, and it'll tell me how many units we have. For example, if my mass of these paper clips is 888 grams, well, we know that each unit is 8 grams, so overall we could calculate that there's 111 units, and that'll tell us therefore how many paper clips we have. So again, it's a lot easier when we package our small items into units, and if we know the unit mass. And again, we do the same thing, or we can do what I just described with atoms. Particularly for water, the unit mass of water is 18 grams, so for every 6 times 10 to the 23, there is 18 grams worth of substance. This unit mass is known as the molar mass. So again, it's the mass for 1 mole of a substance. For water, this happens to be 18 grams. The units for molar mass are grams per mole. So grams divided sign mole, or grams mole to the -1. You have to make sure that you use these units correctly. I'm going to write down a few examples of incorrectly written units, so don't write G per M. G for capital M, Gm minus 1. You'll notice that in chemistry there's a lot of things that start with M, and we need to be very specific in writing MOL for moles. So how do you calculate molar mass is our next question. What we basically do to calculate the molar mass of a compound is to add up all of the molar masses of the atoms. So if you take a look over here, what I'm going to do is I'm going to calculate the molar mass of water. So again, all I have to do is sum, so that sigma, that capital sigma, is a sum sign, the sum of the atomic masses. Okay, where do I find the atomic masses? In the periodic table. So again, I'm going to write molar mass, I'm going to write H2O, so we remember what chemical I'm looking for. To figure that out, all we do is we add the molar mass of H, plus the molar mass of H, plus the molar mass of O. And again, we have to do that hydrogen molar mass twice because there's 2 hydrogens in H2O. Taking a look at those atomic masses in the periodic table, I have 1 gram per mole for hydrogen, and I'm going to add that twice, and then oxygen is about 16 grams per mole. Adding those all together, I get the molar mass of water. So for every 6 times 10 to the 23 atoms, we have 18 grams of water. You try it out with NH3. Okay, so let's put it all together. Let's say we want to convert from mass to moles and number of particles. So again, when we're trying to figure out how many moles, how many packets we have in a certain mass, we divide the mass that we have by the molar mass that can be found by adding the atomic masses in the periodic table. When we want to go the other way, we multiply. When we want to go from the number of moles, so again, that packet, to the number of particles, what we can do is we can multiply by Avogadro's number, multiply by Na. When we want to go the other way, number of particles to moles, we divide by Avogadro's number, again 6.02 times 10 to the 23.